Great. My name is Joe Jasinski, and I'm going to be talking about making it so simple by streamlining your web development apps. So first of all, we love technology. That's why we're here. And there's a lot of different types of technologies. And it's our job as technologists to be familiar with a lot of them. So, but we also have to remember that there's costs associated with this technology. You might be like, what do you mean costs? This is open source technology, it's free, right? Well, sort of. What are some of these costs? Well, actually running the applications, you got CPU, RAM, disk space, that all takes up some sort of cost in some cloud or physical machine somewhere. Backups, that takes up space and time. Monitoring takes up space. You got to set that up and have storage for that. Logging, that costs a lot of stuff. The time it takes to develop and implement, the time it takes to automate all of the deployment of that such, including the number of teammates that do it. So if someone leaves, you have redundancy. Support of the new service. I mean, sometimes that service is going to be taking up something that's probably going to page you because it's going to fill up space, or there might be networking issues or whatever. So, and there's probably more that I didn't think of, but there's costs of this stuff. So one question to ask yourself is this new service really worth all of this? It might be, it might not be. Are you going to need all of the stuff that it does? Is it too complicated for what you need to do? What about looking closer to home? By the way, these were the other generated images. ChatGPT is not very good at generating windows. Like, if you notice, the curtains are on the outside of the windows in a lot of these. So here's the goal for this talk. I want to make a case for simplifying your applications by using something you already have. And I want to show some examples of how I've saved some time by thinking closer to home. So let's come up with a real world scenario here. So John Luke Pritchard is a famous captain from the Space Fleet, just retired from his active duty and wants to set up a real estate company. And he's hired you to help him build a website for this real estate company. So John Luke has some user stories that he wants you to help him out with. Make it so I can store listings in a database. Make it so I can show the rooms in each listing and search for these listings with certain properties of a room, such as a room color. Make it so I can do a full text search of the listing and name and description. Make it so I can search for listings within a certain radius of where I am. And make it so that only one person can schedule a visitation with a realtor at a given time. So, okay, for this talk, we're going to use some space-age technologies, including Postgres and SQLAlchemy. Now, this was part of the title of the talk, so you should know this already, but this isn't a deep dive, but it's just going to be kind of a problem-oriented set of examples here. So Postgres, most of you probably know what this is, but it's a powerful open source database, been around since the early 90s, and it has lineage back even to the 80s. It's very featureful, it's an ACID database, very production ready, used in a lot of different contexts, and it's more and more popular every day. SQLAlchemy is a open source Python toolkit for interacting with databases. It supports multiple different databases backends, including Postgres. So the idea is you can generate queries for one database backend and more or less be able to run it with a different database backend, like MySQL or SQL Server or whatever. It allows you to generate SQL in a Pythonic way instead of dealing with strings and kind of like mushing and managing strings of a SQL statement together. You can write it as Python objects, which makes it a lot easier to compose different SQL statements and generate them. And it also includes an ORM, or object relational mapper, which allows you to represent database records as objects. So let's take a look at these user stories. Make it so I can store listings in a database. So this is pretty straightforward. It's show you just to get us started with SQLAlchemy, a basic example of creating some records. So I'm going to run some cells here in my Jupyter notebook. But here's where we start with SQLAlchemy. For example, this is creating a database engine, which basically establishes a connection to the database, and it's like object that holds the database connection. And next, we're going to create a database table called listings. This is going to be the name that's actually inside the database, and this is the Python object name. It's got an ID column that's an integer, and it's a primary key column, so auto-generate primary keys. It's got a name, which is a string, and the string has to be unique. It's got a created at and updated at timestamp. So whenever you create the record or update it, it will update the record in the database. And so this command here, I'm just deleting the table just for this demo, so I can like delete and recreate it all the time. You normally won't run this. But this command here is what creates the table for you, at least when we're talking about the SQLAlchemy or ORM context. So there we go. I just created the table. Now let's add some records to it. Now this is pretty straightforward. I create a database session, which basically opens up a connection to the database using the engine. I'm going to add these objects, these listings, and provide a name to them. And in doing so, we'll start a transaction. When I run commit, that transaction will be atomically commit those records all at once to the database. So here we go. I added some records to the database. And now I have this little extension inside of Jupyter Hub. By the way, I forgot to ask, is this enough? Can you see this? You want me to make it bigger? One more bigger? Okay. All right, good. Yeah. Yeah, so actually I can show you that later, but right now I'm running this as a Docker container. I'm running the Postgres Docker image, and then Jupyter Notebook in a different Docker image. And I've actually have this posted online, so I can link you to an example of setting that up. So this extension here is just a handy little Jupyter Hub extension that lets you do direct queries to the database. So just so we can debug it and like view what's happening as we're doing the SQLAlchemy code to it. So I'm running here, this is a simple select statement, select star from listings, and we see that these two records were added. This is basically the equivalent of doing a select star inside of SQLAlchemy. So I'm doing select listing. I mean, that's all you need in this case here is just do select listings, and then I run it, and it generates the SQL select star, listing ID, listing name, created at, updated at, basically select star from listings, and it returns these listing objects. Now I created this little run query function just for convenience. That's defined up here just to show you it's nothing magic, but I'm passing in an engine, a query, and the scalar is equal true. It will create a little database session. If scalar is equals true, then it's going to run and return to me the database objects, the listing objects. Or if I run just the session execute with scalars equals false, it's going to return tuples, just regular database record tuples. So I'll show you an example of that in just a second. So here we go. As you can see, scalars equals true, the default, so I'm getting database listings back. And here's a similar query, except now I'm being very explicit about the columns names. I just want to select the ID and the name. And here I'm setting scalars equals false. So I'm getting tuples back. So you can see it's returning back one, or the ID is one, the name, two, the name, and it's running the SQL statement. And I can combine this also with a filter. So I can do select listing ID named and only return listings whose name is Addison. And I can do the same query, select listing ID names from listings where listing name equals Addison, and I get the one record back. So that's pretty straightforward. And we've accomplished that goal. We've satisfied that user story for Captain Pritchard. Let's take a look at our next requirement here. So make it so I can show the rooms in each listing and search for listings with certain properties of a room. For example, room color. So every house is different. Every house has a different number of rooms. And I want to store, I don't want to have a separate relationship with all these listings for something that's only going to be relevant to that room. So one thing I've seen on real estate websites is you have a set of rooms, and it might have living room, size, color, whatever. It just properties on it, and it's like a dynamic list depending on the listing. So I want something like that, and JSON would probably be a good way to do that. And we want to be able to search these properties. So we can have like cool filters, or people can find rooms and properties that they like. So should we use Mongo or something similar? Mongo is pretty good with that. Nah, Postgres can do it. So we're going to use something called the JSON-B field, the binary JSON field, basically. So if we take a look at this JSON-B example, I'm going to modify the listing table here. And this looks the same, except I've added this new rooms column with a type of JSON-B and another type of JSON-B there. So everything else is the same. So I just created that table. And now I'm going to just create a few more listing objects, and I'm going to define a few rooms for each, a rooms property that I pass in for like kitchen, color equals blue, bathroom, color equals green, and so on and so forth. Now you could put whatever you want in here, but for this example, I'm just going to use colors just for simplicity. So if I run this, yeah, I know, right? The sound, oh, there we go. Here, if I run the select statement again, just to see what was inserted, we've got the name, and here's what the JSON looks like. It looks like JSON. So now let's say I want to find listings with bathrooms, because in Illinois, if you, for example, if you take your toilet out of your bathroom, you don't have a bathroom. So we want to exclude that. We want to find properties with a bathroom. So actually, here we go. So here's how we do that. Basically, we do rooms has key bathroom. If I render that, it renders it out into the SQL statement here. And this is like a special syntax for querying JSON data, where basically it is that key present. And so it's going to return for me all of these listings with a bathroom. And you can see listing number 6, which we had up here, doesn't have a bathroom, so it doesn't return it. Cool. So this operator is doing the same thing as the above syntax, and it generates the same SQL query. And with this here, it's just another way to do it. Maybe a little bit more expressive if you need to get more complicated. And here's what that looks like if you're just running the raw SQL. You can see that it's filtering out only the records that have a bathroom attached to them. Or let's say we want to have a bedroom that's yellow. So find me all the listings with a yellow bedroom. And basically it's pretty straightforward. You're kind of like looking for the keys, bedroom and color, and converting that to text, and returning yellow, or matching anything that equals yellow. And you can see this diversity one, number 2, is has a yellow bathroom, or yellow bedroom is what we were looking for. So here's the same query, just written in the SQLAlchemy way. And these arrows have special syntax too. I believe it means that if the stuff on the right, the single arrow means that compare the listing rooms and look for a JSON object with the named bathroom. Like it thinks this is JSON. And then this operator here with the double arrow means that it's converting that to, expects it to be in text. And so again, we're doing this basically the same query as this one, just with a more SQLAlchemy style syntax. And so, yeah, here's the query, again, run directly. And here's another way to do it, where I can just literally look for color equals yellow in the bedroom object. And here we get that same result. And you can see that there's more than one key inside of this JSON dictionary, but it did find the one where it did find all the records with color equals yellow for the bedroom. You can do not null searches. So is there a bathroom that is null or not null? So I can run these, and it's doing these similar queries here. Here's the SQL version of that. I could search for, let's see, does the kitchen have a color? Like, it doesn't matter, like I'm not looking for the fact that it's yellow, but I'm looking for any color. So I can query that. Or does the garage have a color? There is no garage. So it just returns an empty set like you'd expect. Or here's a more complicated example. Find all rooms with a green color. Now, JSON path is kind of a separate syntax, a separate project that lets you define like very complicated queries for searching a JSON dictionary or JSON object. And I don't claim to know all of this stuff, but you can use the very powerful JSON path syntax to query out more robust queries. In this case, I'm querying for any record where there's any color that's yellow, any room with a yellow color. And so the cool thing about this is these JSONB, like Postgres has a lot of different JSONB functions built in, like this JSONB path exists. It's got a ton of them, so it's very powerful and very robust. Here I can also use, the JSONB query syntax in the select portion. So I can return I could do a select and I can return the subsets of the JSON dictionary or whatever my query is, I can have it be part of the select. And that's what it looks like when doing the raw query. So great, we've got the ability to add rooms to our listings. We can search them, so we can expose that to the users and they could have, they could search for all sorts of different properties about their listing. And that satisfies the second requirement. There you go. Yeah.
JSONB column. How did you specify a JSONB column in SQLAlchemy?
Yeah, it's literally just like you import the JSONB data type and you literally specify that as the type, just like you would a string or an integer. Instead, you give it that JSONB object. And here I can, well, maybe I can show you after because, no, that's good. Appreciate the question. Okay, so make it so I can do a full text search of listings. So I can search name and description. So we want to be able to search the title and description or the name and the description. We don't want to have an exact match for our search terms. Should we use Elasticsearch? That's a pretty powerful tool. We can, but we don't have to. Yeah.
Particular reason of why we're not doing it solely within Postgres, because so far it would seem like it would be easier.
So the reason why you wouldn't use it in Postgres is because, like I said, doing the string manipulations is kind of onerous. And if you could represent all that stuff as objects, it just makes it easier to compose and like add different filters to your queries. And you're not having to deal with syntax editing of the queries themselves. That syntax is all taken care of for you already by the SQLAlchemy rendering engine. And there's other reasons too, not for this specifically, but if you want to have a different database backend, some of this uses Postgres specific functions. But for the most part, SQLAlchemy is pretty database agnostic unless you're using those Postgres functions. So you could literally swap it out with SQLite or MySQL or whatever. Like if you're developing, you could use SQLite. And then also it does some security for you. So it does some auto escaping. So you're not like so susceptible to like SQL injection attacks. So there's a few things along those. Yeah.
I have a question, but I'll add one more. Is if it's in the context of a web app too, like you can't just if you can closely couple your database with your application too. So if you're like changing columns, like you make sure that doesn't break your web app. If you're doing that in raw SQL, probably break your app.
Yeah.
Minor question. Those look like pandas data frames. Was that magic you added, or is that just coming out of the SQLAlchemy, or
the pandas data frames? Let's see.
In your notebook outputs?
Let's see. Oh, wait.
Yeah, like that table. Right?
This here. Oh,
the output. Yeah.
Oh, so this, the SQL Magic, like you said.
Oh, okay.
It's just a plugin that renders it nicely, so it
nice.
renders it kind of like a data frame.
Cool, nice.
But it's kind of handy. So, all right, so I guess, yeah, we're back to the demo for full text search. So what we can do, what SQLAlchemy has is this concept of like a TS vector, which is basically, you can give it a string and then convert it into essentially like an index vector. And so, for example, if I run this here, it takes this string and removes any what they call stop words, any words that are like irrelevant for, like you'd never search for I or my is. It's not really going to provide any useful results. So there's a bunch of stop words that are defined to remove all that stuff. And then it like lowercases everything for certain words, it destems them. So if you have like a working or fighting, it would take the stem out. So it kind of normalizes this and indexes it. And I don't claim to know exactly how it's like representing this, but you can kind of see it's going through here and, kind of shortening it and normalizing it a bit. And similarly, you could use this double ampersand syntax to issue a query against that vector. So that's this 2TS query takes this string here and compares it against the string that's been vectorized. So if I do that, it will return like is Chicago and Django inside of the string, and yes, both of them are, so it returns true. Or if I go Ruby, it'll say no because it's not. But if I do or, it'll say yeah, Chicago's there, but Ruby isn't. So here's kind of like the same query. Food isn't in this query. So I can add a TS vector to the SQLAlchemy table that we're building up, this listings table. And it looks a little bit more complicated, but really it's kind of doing the same thing we just saw. Essentially, it takes a column of type TS vector, and it does this thing, this creates what's called a computed column, or you can create it with a computed column, which basically is a dynamic column that whenever you it'll take other inputs, other fields, and you can convert it into something that this column represents. And this persisted equals true means that this TS vector will actually appear as a column on the table. And so whenever I change, something that's name or description field, it's going to recalculate this TS vector field as well with those vectors and then store it to that table. So a few things here to note. This is very similar to what we saw before. We're doing a little bit of casting and all that kind of stuff. But basically, we're doing this TS vector on the name field and the TS vector on the description field. And then additionally, the set weight is a feature that lets you prioritize searches for like the name over the description. So A takes precedence over B. I'm not particularly satisfied with the syntax, but it's something basic enough, and it works pretty well for what it does. So so let's create this table here. And then I'm going to add some descriptions, some listings with descriptions in them. Query that. And so you can see here, the name is home, the description is this, and then there's a vector like this. It vectorizes the name of the description, and it assigns the weights to them, A and B, just like you see here. And then you can run a query against this by doing this, the similar syntax where I go select listing, filter listing where TS vector, the TS vector field contains the this query, this search query, yellow house. So if I run that, it's going to, it returns this listing here, listing number 2, which, sure enough, it has yellow and house in the text. Here's the same thing in SQL. Here's where I'm putting some OR statements in there. This is a different type of query, but where, just like we saw before, it's searching for anything with house or yellow or country. And each of these records contain at least one of those things in the name or description. And that's the SQL version of that. Oh, maybe I used on the next slide, but. So, all right, we got that requirement done. Now, we want to make it so we can search for listings within a certain radius of our current position. So, I want to search for listings in my area. I want to be within a certain radius. we could use Google Map for that, right? But we don't have to. We can use Postgres. We can use what's known as a geometry field. So basically, Postgres has this really powerful plugin called PostGIS. It's an extension. You can basically apt-get install it if you're on Ubuntu, or there's other, probably yum install it with Red Hat. But then Postgres, you run this create extension command to like activate it within the current database. And then we take this existing listing field, or the listing table that we were looking at before, and I added this geolocation column, which takes an optional, well-known binary element. That's what they call this geospatial text. And it's of type geometry and a point. And this SGrid is like the coordinate system, like this common coordinate system that we're using, and we're adding a spatial index so it can perform it quickly. And then also here's, well, that's for the TS vector. But so that's basically all that I'm adding for this this table here. And now I'm going to add some new points to it. So here's the location of each of these places, and these are points all around Chicago. So I created that, and then here is, you can see it did something. It inserted some sort of binary version of those points that we just inserted. Probably that's what the well-known binary is, how it looks. And now we want to do a quick query of that. And basically we want to compare the point inside the database with some other arbitrary point, like this latitude and longitude point. And we want to search within this radius. And now PostGIS has a ton of different functions that's as part of those extensions, like std within, distance within, or st set sgrid, or make point. Just all these functions, there's probably dozens of them, if not hundreds, that lets you do different types of comparisons and spatial geometries. Like you can search within like a shape, like for points within a shape. You can search, like radius and a whole bunch of different stuff. There's like, you can do rasterized searches for searching, like for image representations of geometry. But anyway, so this one here, we're doing a simple select distance within. We're comparing the current listing point geography, and we're comparing that to like a point that we create using this latitude and longitude, and we're looking for anything within this radius, 800 meters or 8,000 meters. So if I run that, we can see here, it generates this query, and we get these responses back. Now, obviously, like you can improve that, but what we can also do is we can return the distance, the ST distance between that geopoint and the latitude, longitude that we specified. We can use this function to do select and give you the distance back, and then only return the ones that are within that radius as well. So if I run that, then we see like the third index is named far, and it's got a distance of 7,600 meters. And shelter the distance is 0 meters. It's because it's the same exact point. Here's how it looks in the Postgres database here. So that gives us a lot of power for doing spatial queries, and that satisfies that requirement. So finally, we want to make it so one and only one person can schedule a visitation with a realtor at any given time. So if two people are in the process of like filling out the form to schedule a realtor, we want to make sure that that they can't conflict and they can't both get a time slot. So basically, yeah, two people should not be able to schedule the same realtor appointment at the same time. And we could create some sort of like distributed locking system with Redis. We don't have to. This Postgres can do it with advisory locks. So basically, remember how I mentioned that like Postgres, there's a bunch of different types of advisory locks, but the one I'm going to talk about here is called like a transactional based advisory lock. So this kind of breaks the metaphor a little bit, but it's just kind of a generic example of how you can create this advisory lock, where you can create a context manager. This is one way to do it, where the key to this is this Postgres function called PG try advisory transaction lock. And what that does is that, remember how I mentioned when you create a session, it automatically starts a transaction. And that's where you can start adding objects and adding, deleting, updating, whatever you want to do. And then when you write commit, it commits that transaction all at once. And then you can it starts a new transaction, so you can start doing new stuff. Well, the advisory lock uses that functionality. So basically you can say, for this transaction, I want to lock this resource, and the resource being the name of the lock value, which is like some string that's like a common string, like an ID of a listing, or the date and ID of a listing, whatever you want to lock, so two people can't access something that represents a resource that you don't want two people to access at the same time. So that you'd give it this lock value. This code hashes that text and then passes it into this advisory lock. So basically, two people can't hold on to this lock, this string lock at the same time. And here's how you kind of implement that. You use the context manager, create a session. You pass in the session to the context manager, the lock value, some unique string value. Again, it could be an ID. And then this advisory lock will return this little data class that I created called lock. And it will just say whether or not it's locked or not. And if it's locked, then we skip it. If it's not locked, then we can attain the lock through the advisory lock, or then it automatically attains the lock, and we can execute some important SQL that takes some time, or we want to make sure to protect. So here's like an example of that, how that might function. So when I run this, it's going to wait for 30 seconds to kind of simulate the advisory lock. So here it's spinning for 30 seconds, and it says got the lock. So while this is spinning, then this is locked and we can't access it again. And this is the exact same code. I just pulled it out to represent like a second request being made. So if I run this, it says skipped because locked, because this one's got the one on the left's got the lock already. But as soon as that 30 seconds is up, which it should be in just a second. Yep, there it goes. Then I can run this. And this one holds lock. If I try to run this, it says skip because locked. And then that skipped, you can return as an error back to your user and say like, oh, please try again later, or do whatever error handling you want to do. So that kind of helps us make a solution for the last user story. But basically, in summary, you have all these great tools at your disposal. And this is just some examples of a tool that lots of people have, a database that you can leverage before reaching out to other stuff. So I encourage you to look at your tools and learn them, so you don't have to take on new risks, and you can make your clients happy. And if you're interested in the code for this, just Google Joe Jasinski, and then you'll find it as like the newest repository on my GitHub. Joe Jasinski GitHub. I think my SEO is that good. Yep. Yeah, right. So the code for this is right here. Yeah, I can post it in Slack, sure.
So the double at syntax.
Yeah.
So that's like, from my understanding, it's a SQL syntax, but like, will it work across in the Python? Because I saw that you used, without the operator, you use it directly, so it doesn't break the.
I don't think I did that, but let's take a look here. Oops. So we need this search one here. So this here, I was using the plugin. I'm using this directly, but that's because I'm using the Jupyter plugin. But this one here, I'm using the op one before. This again, like this here. Let's see. Yes, so Like this here, again, is a raw SQL query, so I was using it there. I think anytime I've used it, yeah. I mean, as far as like, this is using some features of Postgres. It's using this Postgres dialect.
Okay.
So these TS vectors are Postgres specific. However, like MySQL, it doesn't have quite as many geospatial features, but it does have some. And some SQLite has something like SpatialLite, I think, which you can do geospatial queries there and search. I think MySQL does pretty good full text search. And of all these things, I think the full text search is the weakest. But I have used it in production environments to do some like basic user searches for database records, and it works pretty well for that.
To do that. So if I use a TS vector, let's say if I want to have a fuzzy kind of match, as you said, like Elasticsearch is something that we can definitely use, but like, can I hook in a custom function or a callable in this case to get that thing? Because like if I have something that just calculates the Levenstein distance to the two similar values in my data in my table, can I just show those values in this case by hooking that thing to TS vector or something like that?
I don't think so, but I don't know all the features, but it didn't look super robust. But like I said, it does, like, if you're really trying to get in, like going from here to like Elasticsearch just is like a pretty big jump in terms of stuff you have to implement and consider. So obviously you make that jump when you need to, or if you need to, but until you do, you could do something like this. But I could be wrong. Maybe there's some new features that I'm not aware of that let you add more customization. Oh, nice. Oh, nice. That's great. There's a fuzzy string match function that's built in, so you could use that.